Okay, so here's the situation. This is secant squared, cosine squared, tan squared, and sine squared, right? And if whether they're linearly independent or dependent depends if there exists a C1, C2, C3, and C4, where C1 secant square x plus C2 cosine squared x plus C3 tan square x plus C4 sine squared x equals 0 for non-zero values of C1, C2, C3, and C4, then they would be linearly dependent, correct? Now watch. The right away notice that these two add up to 1 if C2 and C4 are the same. Okay, so if I claim that C2 equals 1 and C4 equals 1, then C2 cosine squared plus C4 sine squared would be 2. I'm sorry, would be 1. Okay, now furthermore, we know that secant squared x equals tan squared x plus 1. Move the tan squared over, so you get secant squared x minus tan squared x equals 1. So for this 1 here to disappear, the sum has to be -1, so I can flip the signs here. So I can make this minus plus minus. Now, so that means if I call the coefficient of secant squared x, which is C1, to be -1, and the coefficient of tan squared, which is C3, to be 1, those two will add up to -1. The sine squared and cosine squared will add up to 1, and therefore the sum will be 0. Because look what's going to happen now. I will get, if I rewrite this, I will get C1, which is minus secant squared x, and C3 is just 1, plus tan squared x. Okay, and then C2 is 1 plus cosine squared x, and C4 is 1, so plus sine squared x. And you could see that these two here are -1, and these two here are +1, and I would indeed get 0. Therefore, there are C1 through C4 that exists where they have those values. C1 is -1, C2 is 1, C4, 3 is 1, and C4 is 1, where the combination would equal 0 for some non-zero values of C1 through C4. Therefore, they are linearly dependent. You understand? So we can write in the conclusion, there exists C1, C2, C3, C4 for at least one of them does not equal 0. There could be 3 0 and 1 non-zero. At least one of them doesn't equal 0, where the combination led to 0. By the combination, I meant, summing them up. By the combination, I meant equation star. So by the combination, I meant equation star. Therefore, secant square x cosine squared x tan squared x and sine squared x are linearly dependent. So this concludes the proof. Trick question. Could you have done this with the Wronskian? Not really. If it was solutions of a differential equation, you could have done that with the Wronskian. But if you have functions, and if you suspect that they're linearly dependent, you have to prove them by the definition. You can't use the Wronskian to prove that they're linearly dependent. You can use the Wronskian to prove that they're linearly independent.
Yeah.
But you can't use it to prove that they're linearly dependent.
Right.
Because in this case, you will get 0, and if the Wronskian is 0, that doesn't automatically mean it's linearly dependent. You have to be careful how to use the theorem.
Yeah. Yeah, because